What's up, everyone? Today we're going to focus on how we can find the equation of the inverse of a function, okay? We've already talked about if you're given a small set of ordered pairs, a discrete relation or a discrete function, you can find the inverse by simply switching the x and y coordinates of each one of those ordered pairs, right? But now, what if we're working with a continuous function where there's an infinite amount of points? You can't possibly write down an infinite amount of ordered pairs, right? So that's where equations come into play, okay? So if I am trying to find the equation for the inverse of a function, all I really have to do is switch the x and the y coordinate within my equation, and then I want to solve that back for y. Okay, we always like our equations to be solved for y so that y is the dependent variable and x is the independent variable. Okay, so let's try to find the inverse of the function f of x here over to the left. It's a linear function. F of x equals 2x minus 3. Now remember, f of x is just a fancy way of writing y. It's a notation that stands for y. Okay. So if I want to find the inverse, I am going to switch the position of x and y in my equation, and then I'm going to think about how I can solve this back for y. Technically, x equals 2y minus 3. It is an equation for the inverse. We just need y to be thought of as the dependent variable and x to be the independent. Right now, it's the opposite. So I'm going to add 3 to both sides. That's going to give me x plus 3 equals 2y. And then I'm going to divide both sides by 2. And let's reverse everything here. I'm going to say that y equals 1/2 x plus 3/2. There's my inverse, and then I'm going to finish off by using inverse notation here. Instead of y, I'm going to write this as the inverse of f of x equals 1/2 x plus 3/2. Okay. All right, now let's do the same thing for g of x. G of x is a quadratic function here. Once again, I'll think of this as y equals x squared minus 3. To find its inverse, switch the position of x and y. And now we want to solve it back for y. Add 3 to both sides. So I end up with x plus 3 equals y squared. And now to get y alone, I'm going to have to square root both sides. Okay, once again, I'll reverse everything here. I'll say y equals, now don't forget when you square root both sides, you technically need plus or minus, right? Y equals plus or minus the square root of x plus 3. So notice the inverse of a squared function, a quadratic function, is a square root function. Okay? And let's finish off. We'll use that function notation one more time. So I'll use the inverse of g of x. It's plus or minus the square root of x plus 3. Okay? All right, moving on to the next tab here. So this brings us to a property associated with inverses. There's a couple properties we'll look at over the next couple days. So this property is stating that a relation and its inverse are always going to be reflections across or about the line y equals x. Okay, y equals x is the identity function. So if you look at the picture over on the right-hand side here, y equals x is that dashed yellow golden line there. So it's a linear equation with a y-intercept of 0 and a slope of 1. Any point that's on that line, the x coordinate would be the same as the y coordinate, right? And notice the functions f of x and the inverse of f of x, those are reflections across that line. Also notice where they intersect each other. They intersect each other at points on the line of y equals x. Okay, so that's an interesting property for inverse functions. All right, so we're going to use that property in this example below. We have the graph of f of x equals 2x minus 3 shown. That's the blue line here. Okay, let me label that. This is f of x. And we want to graph the inverse and then verify with the equation we found for the inverse back in example 3. If you notice, this is the same function as back here. Okay? So all we need to do is pick a few random points that are on the original function f of x. So I'm going to pick that as a point right there. That's the point of 2, 1. I'm going to place another point here. That's 3, 3. And then how about one more for good measure right here? That is 1, negative 1. All right, now we know that the inverse function, it's going to include points that are just switching the x and the y coordinates from the 3 that I found here, right? So if I do that with 3, 3, that's going to stay put. 2, 1 would now become 1, 2. And then 1, negative 1 is now negative 1, positive 1. Okay, and then we can draw in the new line here. We'll label that as the inverse of f. And notice we do have a reflection of the green line and the blue line across y equals x, which is the red dashed line there. Okay, so let's verify the green line. Back in example 3, we said that the inverse of f of x should equal 1/2 x plus 3 halves, right? And I think that line does in fact match. If you locate the slope of that line from point to point, up 1, right 2, and then notice the y-intercept right here, that appears to be about at 3 halves or 1.5. Okay? All right, click over to practice 3. Now it's your turn. You're going to find the inverse of this function g of x. Make sure you solve it for y. And then you're going to verify it. You can click on the link there to go to Desmos. You're going to type in the equation for g of x. You're also going to type in your equation for the inverse of g of x. And thirdly, type in an equation for y equals x. Make sure that your two equations are reflections across that line of y equals x, right? Another way you can check is by using the box down at the bottom there, or the table down at the bottom, to type in your equation. If you do it correctly, the red will turn to green.